The overall goal of this procedure is to manipulate cells and beads within microfluidic devices using dielectrophoresis, or DEP, using printed circuit boards, or PCBs. This is accomplished by first designing and preparing the PCB electrodes and microfluidic channels. The second step of the procedure is to prepare the PCB microfluidic assembly and the bead and cell solutions. The third step of the procedure is to fill the channels with low conductivity media, then load the beads and cells. The final step of the procedure is to connect the PCB assembly with the power amplifier and function generator and then initiate DEP. Ultimately, results can be obtained that show the separation and manipulation of cells and beads in microfluidic devices through the use of DEP.
Generally, individuals new to this method will struggle because the principles of DEP must be understood by the user in order to develop an effective electrode that works with microfluidic device for the desired cell or bead manipulation. On the other hand, using PCBs as electrodes makes cell and bead actuation in microfluidic devices approachable to a range of scientific disciplines.
The first step of this procedure is to design the printed circuit board, or PCB electrodes, to have the desired geometry to generate a non-uniform electrical field. When the design is complete, order the customized PCB electrode chips through a commercial fabrication facility. After the custom-made PCB arrives, open it and inspect it. For this demonstration, the PCB is 8.4 centimeters long and 2.1 centimeters wide. The metal electrodes are 5 millimeters wide. In this example, the electrodes have two long metal strips and two 4.5 mm long cross regions where the electrodes are interdigitated. These interdigitated regions generate a strong non-uniform electric field. To create a connection from the stimulator to the PCB electrode, place a 16-gauge wire onto the end of the electrode. Use a hot soldering iron to hold the wire in place on the metal area of the PCB. This heats the wire. Hold the solder to the heated wire and allow a small amount of solder to flow into the wire. After the wire is filled with solder, remove the soldering iron, holding the wire in place while the solder cools. Repeat the soldering process for the other electrical connection on the PCB. The next step is to prepare microfluidic channels with the desired branching pattern. Using standard microfabrication techniques, create a master mold to define the channels using a silicon wafer and SU8 photoresist. This master mold has one input channel and 3 target channels. The width of the channels is 100 micrometers and the height of the channels is 27 micrometers. Once the master mold is created, mix the polydimethylsiloxane, or PDMS, elastomer with a curing agent at a 10:1 weight-for-weight ratio for 5 minutes. Pour the liquid PDMS onto the prefabricated SU8 master mold and remove air bubbles by exposing the liquid PDMS to a vacuum for 3 minutes. Repeat the vacuum process if needed to completely remove all bubbles. A stream of nitrogen gas can be used to remove extra bubbles if needed. Cure the PDMS in an oven at 70 degrees Celsius for 2 hours. Use a razor blade to remove the PDMS slab with the microfluidic channels from the wafer, being careful not to break the wafer. With the channel space up, use a biopsy punch to punch holes for introducing fluids and cells into the microfluidic device. Trim any excess PDMS. Inspect the microfluidic device to ensure that it is free of dust and debris. Use 3M Scotch Magic Tape to clean the PDMS. Expose the PDMS channels and a clean number 0 cover slip, 80 to 130 micrometer thickness, to plasma gas for 1.5 minutes. Remove the PDMS slab and the cover slip from the plasma cleaner. In a petri dish, plasma bond the PDMS microfluidic channels face down on the cover slip. Heat the cover slip microfluidic assembly on a hot plate set at 100 degrees Celsius for a minimum of 15 minutes. The final step in preparing the microfluidic device is to position the PDMS channels and cover slip above the electrodes of the PCB. Start by placing approximately 10 microliters of mineral oil onto the PCB to ensure tight contact between the PCB and the cover slip. Place the cover slip microfluidic channel assembly onto the oiled PCB with the cover slip contacting the oil. Gently press the cover slip microfluidic assembly down to ensure a good contact and to minimize air bubbles that can detract from cell and bead visualization. Another important step is to prepare the low conductivity media. Mix 8.5% sucrose and 0.3% glucose weight to volume in deionized water. The microfluidic device is now ready for use. Using a pipette, fill each microfluidic channel with 15 to 20 microliters of the low conductivity media. If necessary, use vacuum aspiration to remove any bubbles in the channels. The next step is to introduce the test particles into the microfluidic device. This demonstration uses a suspension of 550 polystyrene beads per microliter of low conductivity media. As the beads can settle out over time, resuspend the beads with agitation. Then, using a pipette, introduce 200 microliters of the polystyrene bead suspension into the channel. The next step is to prepare the electrodes. Connect the output of a function generator to the input of an AC power amplifier. Then connect the output of the amplifier to the electrode wires. Cover all electrical wires and surfaces of the setup with electrical tape to protect users from potential exposure to shock. Set the function generator to produce a sine wave output of 1 to 1.5 MHz. Initiate DEP to begin sorting the cells and beads. In this setup, the inlet channel is to the right and the 3 target channels separate at the trifurcated junction. The PCB electrodes correspond to the black stripes. Without laminar flow and without DEP, the beads are essentially stationary. Upon DEP initiation, but without flow, the beads migrate toward the PCB electrodes and away from the space between the electrodes. When the laminar flow is on, but the DEP is off, beads flowing through the inlet channels are divided between the 3 target channels. When DEP is initiated and laminar flow is on, the beads are actuated to flow only in the central channel. In the next videos, the microfluidic device was rotated above the PCB electrodes, resulting in a change in orientation of the channels with respect to the PCB electrodes. The inlet channel, which had previously been perpendicular to the PCB electrodes, is now almost parallel to the electrodes. With the laminar flow on but DEP off, the beads enter all 3 target channels equally. When DEP is initiated, the beads approach the trifurcation point and the DEP force pulls the beads into the side channel above the electrode. This next set of figures and video shows a mixture of human colon adenocarcinoma or HT29 cells and fluorescent beads in the microfluidic device. In this DIC image, the open arrow identifies the direction of laminar flow and the channels are outlined with dashed lines. The reflective metal electrodes can be seen as the light background stripe. DIC microscopy is used to image the beads, while glow-scale intensity images are used to make the cells more visible. This figure is the same image as the other figure, except shown as a glow-scale intensity image so as to visualize the cells as well as the beads. The reflective metal electrodes show as yellow and green stripes in this figure. With DEP, the beads exit the right channel as shown in the DIC image, whereas the HT29 cells exit the central and left channel as shown in the glow-scale image. Prior to initiating DEP, a mixed solution of cells and beads flow from the 1 inlet channel to the 3 separate target channels. After inducing DEP, the beads and cells are selectively actuated into separate channels.
After watching this video, you should have a good understanding of how to begin implementing dielectrophoresis for the manipulation of cells and beads within microfluidic devices.